Hey David, wanted to send you an update on what we're doing with the test prototype model. As you can see, I've got it set up here. We've got the controls hooked up to it. We've got it pressurized, so I'm going to go through some motions, but just explain what's going on with the different components and what we're doing. So, first of all, this is a pneumatic powered unit, as you know. We've got the air compressor over here. That supplies the pressure to the cylinder that gives us our lift force. Down here we have the actual cylinder that lifts the carriage that has the seat and the backrest on it. Over here we have the directional control valve. That's what basically gives, switches the air to the bottom or the top of the cylinder to make it go up or down. And the pressure to that is controlled by this pressure regulator. It has the air coming in, it has a signal from the programmable controller, and it has the air going out. Now let's go up here to the actual control panel. What we have here is an HMI, which is a human to machine interface acronym. It's a touchscreen panel for directing and controlling this machine. Okay, on here you can see a few things. These up and down arrows are for adjusting the lift force to the seat, to the carriage, to help the patient up and down. Right now it's set at 40 pounds of lift. So when I actuate that cylinder, it's going to lift upward with 40 pounds. Let's go up and down a couple times. You can see that. Okay. This is the whole carriage, the cylinder's connected to it, but what you're going to see going up and down is basically the seat. So with 40 pounds of lift force, we're going to go up to a set height, and then we'll go down. So that's the basic motion. All right. Now, in addition to that, we have a position sensor. Let me go to another screen to show you what I'm talking about. Right here where it says seat position, it's currently saying 0 because it's in the bottom position. Let's walk over here and I want to show you what's going on. This linear displacement transducer, right now I just have it clamped to the frame, but it was attached to the carriage. As the carriage goes up, it goes up with it, up and down. Now, if you'll come over here to the screen and look at this number, you can see it goes up and down as the carriage goes up and down. It's a very precise indicator of where we are. I'm going to put this back down. So the two things that we're doing here, one is we are adjusting the amount of lift force depending on what the patient needs, whatever their strength level or their disability is. And we're also monitoring how high up and down it travels. The reason we do that is to limit the range of motion. A lot of times people have very limited range of motion and they can only work within that limit. We don't want to drive them through that limit. As they're rehabilitated, they get stronger and they get a greater range of motion. So what we can do with this is we can set that range of motion and control it. We can also set the lift force and control that. Okay. Let's go back to the screen here. As you can see here, I've got the lift force at 40 pounds. Let's say I want to put 51 pounds up there. If you look down at there, we're basically, for that cylinder size to lift 51 or 40 pounds, I've got to have around 13 psi, which is what that regulator is reading. Now when I go up here, you can watch this. I'm going to enter in up to 51 pounds. force, and that's going to raise the PSI to about 17. This cylinder has a 3 square inch bore, so roughly 3 times the pressure is going to give you the lift force. If you look at this now, you see 17 PSI down there, 51 pounds here. Now I'm talking about lifting with 40 pounds of assist, 51 pounds of assist. We can actually lift with 300 pounds of assist. So a person who is extremely weak can generate very little lift force on their own, would start out with getting as much of their entire body weight lifted up and just going through range of motion exercise. As they get some ability to push with their own lower body, we would start to lower that assist. At some point, the assist goes to 0 and they can do it by themselves. They're fully rehabilitated. Okay. All right, that kind of wraps it up for this model. The purpose of this model is for us to test, experiment, verify different things, put weights on it, look at how we can improve ergonomics, that type of thing. But our ultimate objective is the advanced clinical model. That's what's currently on the drawing board, and we've already ordered some parts and we're beginning to build that. So the next update will probably be showing you that. Let me explain. I made some notes here. So what is the advanced clinical model? How is it different from this? Number one, it's not driven by pneumatics. There's some advantages to that. The biggest advantages are you don't need an air compressor. You just plug it into the wall. It's all electronic because this pneumatics is going to be replaced with a DC servo drive. The other advantage to that, in addition to not having to have an air compressor, which is easy here in a shop, but not necessarily in a clinic or someone's home, is you just plug it into the wall and everything's powered up. The drive, the controls, the whole thing. So that's where we're going with that. We're also adding here the path of this lift is linear, straight up, and not straight up and down. It's declined a little bit, but it just goes up and down, which is fine. But we actually have begun to experiment with and have designed out a more biomechanically improved motion. And what that means is a few things will be going on. In addition to this carriage being lifted, the seat back can recline or incline. The headrest that will be here can do the same. The seat, as you come to a standing point, you can't stand up all the way. And this is a sit to stand rehab trainer. So the seat has to begin to fall out of the way as you reach the standing position. All of those motions and the ankle angle with the foot plate, all of those motions are controlled and synchronized into one smooth motion. And the reason for that is that the patient, does not have to adapt themselves to the motions of the machine. The motions of the machine conforms to the body and the body motions that are natural, biomechanically natural. Okay. In addition to that, we're going to be working on the ergonomics. The backrest is just a flat padded backrest. We'll probably have something that looks more like a chair back with armrests, a headrest that's adjustable. The seat may look like this, probably look like something else, a better seat. And of course we'll have the foot plate to press against. There will be a lot of sensors on it, some safety sensors like a presence sensor. If you're sitting on this and you start going up and you get a wild idea to jump off the machine, it doesn't need to keep moving. So it will sense that you're moving off the machine and it will lock down and it will stop. If you do anything else out of the ordinary, you start to lean over or something like that, it will sense that and it will stop the motion. That's for safety. There'll be other safety things in there too. I mentioned the auto-adaptive process, I want to just say one thing about that, because that's a mouthful. You may not understand what it could mean a lot of things. What that means is the patient in that mode, you can do a manual mode like this, but in that automatic mode, the patient will sit on the machine. It will be adjusted for position because everybody's body's different. Legs are longer, torsos are longer, all that stuff. So it is adjusted to accommodate them. And those settings are saved in the memory of the PLC. So the next time that person gets on the machine, you can just advance it to those settings automatically. So they sit on the machine and they start to push with their feet to raise it up. With the load cells and the position sensors, the machine will be smart enough. The programming is like a smart machine. The programming will recognize from the inputs that they're not moving with all they can push, and it will start to add lift force. Once they start moving, it's looking for a certain velocity. There are recommended velocities that physical therapist studies have shown, and we will be operating within that range. Not too slow, where you're fatiguing yourself unnecessarily, not too fast, where you're getting dynamic loads on your joints. But in that range of motion, it will adjust the amount of lift force to match what you're adding into it to keep you in that speed range through the range of motion that you want. So that's what I mean by that. That's a key advantage of this machine over other things in the market. In addition to that, there's concentric and eccentric modes. There's what I call positive resist or negative assist. We'll probably have a shoulder harness that comes over so that at the point where the person can basically lift their own weight without any help, at that point they'll have to push against an additional weight, a resistance training. And again, we're not trying to make power lifters out of anybody. If you get rehab to that point, you need to go to a gym. But once you get where you can just do your weight, it behooves you to get a little bit stronger before you stop training. In addition to that, the ability to program any customized operation that you want is available just by entering into the program. We would be able to provide those if a physical therapist or a patient directs us into what type of motion sequence they want or what type of sensing they want. That's simply a software program, and we could provide that too. Okay, so I hope that gives you a broad overview of what we're doing. Next time, I hope to be showing you progress on the DC servo controlled clinical unit. And hope you get to feeling better, David.